So for our last lesson, we're going to take a look at finding the derivative of some more complex functions. For instance, in this case, we have the quantity of 3x plus 2x squared, all raised to the fifth, and we want to find the derivative of that. Now, we have the ability to do this, but in not such an easy way. Ideally, all right, with what we know already, we could multiply this term out 5 times, which means foiling, getting a huge, huge term, and then doing the cx to the n, where we go n minus 1 all the time. Total pain. What we'd like to do is make this easier. Now we notice in this function that the quantity of 3x plus 2x squared is within the quantity of some x to the fifth term. All right, now, that's a good thing. All right, it acts like a function within a function, or a composition of functions. So w of x is made up of a composition of 2 functions f and g, where we have, in this case, some f of g of x. All right? When we have that composition, all right, where f of x is like x to the fifth, and g of x is 3x plus 2x squared, again, we call that a composition of functions, and we use something called the chain rule to find the derivative. So what is the chain rule? That's the question of the day, and that's what this lecture is going to be all about. So the chain rule basically says this: if w of x is equal to some f of g of x, then in order to find the derivative, we take the derivative of f of g of x, whatever that looks like, and multiply that by g prime of x. Or, if you have, this is the one I like a little bit better, if you have some f of g of x term, then you let the inner function, or g of x in this case, equal some u term. And then y is going to equal f of some u term rather than f of x. And then in order to find the derivative of y, or the change in y over the change in x, you take the change in y over the change of u, multiply that by the change in u over the change in x. Notice, in this case, that the du's will cancel out, and we're left with du dx. And that's a good thing, once again. All right. So let's apply that to the problem we just done. We see we have that composition of functions that we talked about earlier. We have the inner function, and we have the outer function. So we're going to, in this case, we're going to let y equal some u value to the fifth power, where u represents the innermost function, and u is going to equal 3x plus 2x squared. Now we're going to take the derivative of each of these. This is going to be some change in y over the change in u, all right, which is basically y prime in terms of u. So that's going to be 5u to the fourth. If I take the change in u or the change in x, that's like taking the derivative of u, or u prime, but it's with respect to x. So this goes to 3 plus 4x. Now, once again, multiplying dy du times du dx, the du's are going to go, leaving me with the change in y over the change in x, which is like a slope, right, or the derivative that we know. So I'm going to multiply 5u to the fourth times 3 plus the quantity of 4x. Now, the only thing we have to clean up is this term where we have u to the fourth, because u is in terms of x up here. So I'm going to rewrite this one more time. I'm going to say that dy dx is equal to 5, and instead of u, I'm going to make that substitution of 3x plus 2x squared for u. And that's all going to be multiplied by 3 plus 4x. I think that's a heck of a lot better than multiplying the w of x term out 5 times and then taking the derivative of that. Our next problem looks a little bit different in that it's got a square root, but we can make it look exactly like the last problem. And we also notice that there is a function within a function. One function is the square root. The other function is this 5x to the fourth plus 7. So what I'm going to do is I'm going to say let y equal, instead of w, I don't know, I like using y better, 5x to the fourth plus 7. And rather than put that in a square root, I'm going to raise that to the 1/2 power. So now we can clearly see again we have a function within a function. All right. Here's my inner function, 5x plus 7, and my outer function is the square root or term to the 1/2 power. So at this point, we're going to take and let y equal some u value, and that's the innermost function, to the 1/2, and u will equal that inner function, 5x to the fourth plus 7. dy du, just use the n minus 1 property to find the derivative, so that's a half u to the negative 1/2 power. And du dx is going to equal 20x cubed. Multiplying the two together, I'll do it one more time. The long way, dy du times du dx. Du's go, leaves me with dy dx, which is the change in y, over the change in x, which is the same as the derivative, which is the same as w prime of x. All that junk's the same. Multiply that out, I get a half u to the negative 1/2 times a quantity of 20x cubed. I'm going to make that substitution now for the u value, and in so doing, I'll have my derivative. So I've got, notice how I'm going to do this. I'm going to put my 20x cubed in my numerator. Since in this case, I have a negative exponent of negative 1/2, I'm going to bring that down to the denominator. I'm also going to bring the 2 from the 1/2 into my denominator as well. So, in this case, I'm going to have the following. I'm going to have the 2 down in my denominator, and I'm also going to have my u term, which in this case is the quantity of 5x to the fourth plus 7, all raised to the positive 1/2 now that I've moved it down to the denominator. This will be cleaned up a little bit as 20x cubed over 2 roots of 5x x to the fourth plus 7. And we go to our next problem. Once again, we see we have some function 2x cubed to the third within this whole function. Now, what is the actual function? I want to rewrite it to make it look a little nicer and all on one line. This can be written as -7 over 4 times the quantity of 2x to the negative third, all raised to the -3 power. That's the way I prefer to look at it. So now when we make our substitution, we do the following. We're going to let y equal -7 over 4 u to the -3rd power, because that's like the outside function, if you will. All right? And then u will equal whatever's on the inside. So that's 2x minus 3. The derivative of y with respect to u, or dy du, I'm going to multiply the -3 by the -7 over 4. Gives me a positive 21 over 4. U, subtracting 1 from the power of -3 gets me -4. And the change in u over the change in x, simply equal to 2. Multiply the two together. Notice that's going to give me dy dx, like it has in all the previous problems. I multiply 21 over 4 by 2. The 2 and the 4 reduce to a 21 over 2 u to the -4th. Now I just make one more substitution. It's 21 in my numerator over 2. The u value is 2x minus 3. And since I had a negative exponent, I bring that into my denominator, and the exponent becomes positive. And that's my derivative. Next example. Very similar to last in that it's a root. And I can change that complex radical raised to a power to a single function raised to a power. So I'm going to go from radical form to exponential. We've got the quantity of x squared minus 1 all raised to the 3/5 power. And now it looks pretty much like every other problem we've done. We notice, once again, I have a function, and that function is x squared minus 1 within the function of some quantity to the 3/5 power. And that's exactly what we want to be able to use the chain rule. So the next thing we'll do is we'll take and start making our substitutions. We'll let y equal some u value to the 3/5 power. And u is the innermost function once again, which is x squared minus 1. Change in y over the change in u. And minus 1 rule, 3/5 u. When I subtract 1 from 3/5, I get -2/5. And the change in u over the change in x is simply 2x. Multiplying dy du times du dx gets us dy dx. Gone through that a couple of times already. So dy dx in this case, I'm going to multiply my constant terms, 3/5 and 2 together, giving me 6/5. And then I have the x left, and then I have the u to the -2/5. And I'll clean that up in the next step. Negative 2/5 is going to go down to the denominator. So I'll have 6x over 5. That dealt with the 6/5. And then this negative 2/5 power is going to come down to the denominator. Negative 2/5 power is going to have an index of 5 in my root. And u is x squared minus 1. And then that's going to be quantity squared. And there's my derivative. So that's it. I'd like you to do these two problems. They're very similar to the ones we did earlier today. And if you'll notice, whoops, sorry, I got to get this other problem up for you. See how I do that. Here we go. So pop these in the form, give me the answers, and we'll talk about them tomorrow. Thanks.